I'm live. So I'm gonna do solving this problem and showing it here live. So I'm doing the virtual contest for the Educational Codeforces round 154, and I'm gonna have my try to do this. Okay. Okay. So contest starts. Let's see what we can do. 555. Problem A. Okay. You can brute force this. Oh, hold on. How do I do this? Um, oh, I lost it. It has to contain 2 digits. You cannot promote the sequences of only 2 digits. So only primes that are 2 digits or more are going to be allowed, or will be acceptable. Um, okay. Hmm. Ooh, when would this be impossible? Hmm. I need a way to test if it's prime or not. So, see, you can test if it's prime by checking if it's divisible by anything. Say while. Oh no, just do in range of two. Like even two will work, right? Yeah, two to mm, right. A single digit. Single digits will work because I'm making sure the length is greater than one. So yeah, so for two to int math dot square root of num plus one, import math, and so uh, darn it. Okay, doesn't matter. Return false, right? Let's return true. But see, um, run this real quick. What did I just do? Okay, these are valid though. Like these are primes that you can create from in here. So I think it works. I'm just trying to think if it's gonna be fast enough. It has. How do I do this? Notebooks. I'm probably taking too much time here on this problem, but I've been bit before here. Okay, so let's just run this here. So let's just say 2 to the 9. 2 to 9. What is 2 to the 9? And then the square root of your 9 digits, square root of 10 to the 9 is around 10 to the 5, let's say. So worst case, we have 10 to the 5 iterations. So 10 to the 5 times 512, I, that should pass. That should pass usually. It even gives you 2 seconds. I think I can get away with this. And okay, B, 2 binary strings. Okay, let's look at the pattern here. Okay, how can you do it with this one? I guess this one's easy because you can just select your L and your R to be here, and select your L and R to be here. So you can do it in two operations because that would give you. Okay, what about this one? Okay. The only way to make these two characters equal is to convert this one to 1, which you can't do because you don't have a 1 on the left side. Or you could convert this one to 0. Convert this to 0. Can't do that because I have a 0 over here and a 0 over here. But to do that, you're gonna cause this change. Okay, so you have some string, and let's say you have some. I don't really care what characters are here. Don't care what characters are here or here. But what you have is you have two characters that are the same, and so you can now convert all of these to be x's. So you can create these like groups of consistent characters. So the final string should just be a combination of this, of groups of zeros, groups of ones, groups of zeros, and groups of ones. Not sure if this is gonna work, but I think I have an idea. Um, Okay. From C, queries for the array. I'm, yeah, I'm trying not to compare myself. Yeah, I'm really slow. Okay, queries for the array. Monocarp had an array A. This isn't, wait, uh, this is weird. So hold on. He added three integers and he said, hey, this is sorted. So if you remove two integers, well, it's still sorted, right? Okay, you add an integer, you say it's not sorted. You add an integer, you say it's not sorted. That's impossible because, what was it? If it's less than two elements, it's always considered sorted. You say, it's not sorted, but it's empty. I guess that's true. No, that's still a no. Um, hmm. I guess it's considered sorted again. Every array with less than two elements. Okay, so this one plus zero. What is this one? Yes. This one's explained down here. He adds two integers. He says it's not sorted. Okay, so not stored in, I have two integers, then it's kind of obvious that the first element is greater than the second element. You add another integer, but then you remove that element, then you say it's sorted. That doesn't make sense because I thought you always append to the end and you remove the from the end as well. So wouldn't it be in the same state it was here? So why would it be a 1? Maybe I don't follow. Oh, I'm looking at the wrong one, that's why. It's this one. So they did the add addition, then they subtract. So by subtraction, now it's back in the sorted state. Then they add 1, right? And then they say it's a 1. So this is valid because, yeah, and then subtract 1 and then add 1, say it's 0. Like, obviously that's true. So I'm trying to think. So anytime you spit out a 0, you can assume that in order to transition it to a 1, you have to do at least one subtraction, depending on how many additions. So like here, it does a subtraction, but it does one addition. So you know that, well, you already know there's a 0 here, and then this one is, so you know this one's impossible, already right here. So you don't really care about this, and you know this one is impossible. You can't. So this means you can't pick 0. But you want to calculate the minimum number of operations. So it's a harder problem. Well, this one will take at least 3, because you're gonna have to multiply this one. Um, you're gonna have to multiply this one, this one. Actually, wouldn't this one take 4 operations? How do they do it? Oh, right, you're doing ranges. I don't know why I wasn't thinking of that. So you multiply the range, and then these two will be good. So then you just need to multiply this range, or you could do this range and then this range. This one you could do with, you need to multiply this range. Yeah, you have to multiply this whole range. Hold on. Oh, this is where you can use the negative. So since this isn't strictly decreasing, you can just swap this by using negative here. Then you just need to multiply this one. The debating. I'm thinking I'm gonna try D or C. C I feel like is pretty straightforward. Let's just derive it. But I feel like D might also be straightforward. I don't know. I don't know. I might be wrong here. Okay, so we need to keep track of the length here. I don't know why this doesn't always like work. We need to keep track of the length. Because the length is 0 or 1, it's going to be true. That's a given. If the length is greater than 1, then it could be true or false. So I think so you always check these conditions. You always keep track of the length, and you keep track of if it ever returns a false, boom, it's a no. So and when it's in these scenarios, um, never 0 is allowed. If it's in this scenario, it depends. Okay, let's suppose you have some pluses here, and then you see your first 0. You can assume that the problem was this one, the last element. So you can assume that the problem is at the this length element. So you could like mark it. So you could mark this one or something, right? Yeah, you can assume that this is the problematic element. So then if there is some sequence of pluses here, you have to count how many there are, because and it always has to be a 0, right? It always has to be a 0. So right now you say you're in a state of, why is this is like, it thinks, why does it think? Okay, you're in a state of false, let's say. So the only way to undo a state of false is to go back to the last element that you knew was, so you have like some m, and you know that this is the length where it created that. So the only way you can go from state F to, yeah, the only way you can go from a 0 to a 1 state is if you removed the problem, which is going to be m. So you just have to so you just have to remove that one. So if you have some sequence of pluses, you need to have more sequences, a longer sequence of negatives. So you just have to track the length factor when you know you're in this state. And we can always assume that we're in the one state initially, right? Okay. So from my knowledge, this state is very easy to predict. That is, when you're in a 0 state, you're going to stay in a 0 state. Right? So we're saying if you're in a 0 state, you can stay in a 0 state pretty easily. You can convert to a 1 state, but only given this is only valid if you uh, m, removed m, right? And I don't know what m is. M is just marks the length at which you first entered the zero state, right? Because you always start in a one state. So yeah. Um, okay, so what about when you're in a state one? So you always start in the state one. You can always stay in the state one, right? There's no requirement for that. And you're always going to start in state one. Um, oh, yeah, removed M. And then if you removed M, you can go back to a one. Or does it force you to go back to a one? It doesn't force you to go back to a one. That's true. I need to be careful here. Because you could have a zero, and then you remove some characters, and you still have a zero. You need to update M. So you need to update what you need to keep track of the smallest integer or whatever. I don't know. So you always need to keep track of, you can always push it back based on knowledge in the future. You can always push it back. So if for instance, the string is like, I don't know, like let's say it starts out as a state one, right? We always know state one, and then you don't know when it transitions to state zero. But let's say, oh, you know it transitions to state zero. This represents the length of how many characters that I have. So I have like x1, x2, x3, x4. And so I know it's in state zero after this one. That means I could assume it either transitioned to zero here or it could have transitioned to zero here. But what you can do is you can make this worst assumption that it transitioned to here. And then if you get contradicting information, you can just say, I can always shift it back. Well, that's only if you hadn't already, like, let's say I confirmed that it's false here, let's say, and I didn't make any confirmations on these. So these are actually like unknown in a sense. So I confirmed that it's false here, and I can always reassess this as false too. So as I can always remove an element and say get zero and say, okay, well that's possible because these were in an unknown state, right? So I feel like I should keep an array that tracks what state they're in. So it's going to be true, and then it's going to be like unknown. So it's going to be like x, um, x until there's like some information that comes in. So maybe some information that says it's false or something. Um, but x positions don't really matter. That is, you didn't know what state it was at that point, so it could have been whatever. But if you add more characters, you're gonna have to continue this false, basically. So falses will continue. Um, right? And so you can't be in a state one as long as these elements remain. Okay. Another way to view it is, let me think. I think another way to view it is you could say, like, okay, so you know these falses like this, right? And then you could always get a 1 though. So what does it mean if you get a 1? Say you get a 1 at some point. Let's say you always know it starts as true, and you have some unknowns, and now you hit a 1. What do you do? If you hit a 1, then you have to say that this whole thing is true, right? Because if it's sorted up to here, then it's sorted here, then it's sorted here. So you kind of need to fill that in. So what does this mean? This means that when you mark a certain thing as true, you have to assume that everything else is true. So you can have a variable marking that. Um, and when you mark a false, you have to assume everything greater than it is false, unless you can get back into an unknown state, and then anything is allowed. Having zero after zero doesn't give you any more information because it was false starting from back here, and you know it's going to be false as long as it continues adding. Getting a 1 is true, and getting a 1 and 1 does give you more information because it allows you to backfill. As you can assume, it's been sorted all the way up to here, and so you kind of have to like keep that knowledge unless you delete and then you subtract. Okay, I think I know how to solve this one, so let's code it out. I think max will push it forward if it's less, but it won't do anything if it's greater. Okay, and T, nothing happens to T. Okay. If it's negative, so I just keep it at 1. T equals max of 1. It can't be ever less than T, and you subtract 1. Because T backfills. Okay. And let's see, M, uh, hold on. If size is less than M, oh wait, hold on. Actually, you only want to do this uh, if M is less than size, you don't want to change it, right? M always stays there. It's fixed. Okay. Which this does fix it, right? Because, well, what if M was less? Yeah, that's not good. So when you do plus, when you add a character, you don't want to update m, right? No, you don't want to update m. If you delete a character, you do want to update m. Actually, no. You still don't want to update m. Yeah, missed that at a point. Do you want to update t when you delete a character? Mm, if t was larger, then t is going to get like pushed back, I suppose. Yeah, I think that works. Let's say elif ch equals, okay, so this is where we have to consider. Let's say it's a 0. Okay, so if it's a 0, you need to update m. M will be the min of m and size. Okay. But now you need to check something. You need to check if it's saying that it's sorted. If t, basically, if t is greater or equal to the current size, then just return print no, right? Because that means that you actually, um, that means that, no wait, but if you notice sorted up here, it means it's sorted all the way back here. Yeah, so if you know it's sorted up to a point, then you know it's sorted all the way through the whole thing. So if any size and you delete some characters, you know that was already sorted. Um, so yeah, okay. But you update m to be the min, so that is you can always push m back further. But you can also always like remove m, and I think you can always, yeah. So let's get to the else. So if the else condition is basically, it means it's 0. So if it's 1, you need to check if size is greater than or equal to m, right? Because you say you keep a minimum m, and you have like a certain minimum where uh, you know that m is at this position, right? When you get a 0, you say m is at this position. Um, when you get a true, you can set m. Oh yeah, okay. So if it's acceptable, it's gonna set m to be n again, right? Just set it to some arbitrary max value because if it's true up to this point, you have no false. So the false only happens when you detect a 0, and then it sets the m marker mm, at that point, and then it can go all the way through here, right? False, false, true, true. They can't intersect. I think you can also think of it like as intersection. Yeah, you can think of it as an intersection. So they're going to intersect if t is greater than or equal to size. And they're going to intersect here because here you're going to set t here. So uh, if m was less than or equal to size, then they're going to intersect. But what's interesting is that let's say m was set somewhere further up here. Well, now you're going to set it like really high up because you know that there's no falses remaining here. Okay. But there's another important property because when you subtract characters, if size is ever less than m, if size is less than m, then you need to set m back equal to n because, and yeah, right. Okay. Yeah, you want to do that. Um, and then, so this is correct, I think. And then this is correct. And t like stays the same, right? I think t stays the same when you delete characters. You just have to say, let me think. I think t stays the same. No, t needs to be updated to be the min of 1 and t minus 1 because when you got the confirmation of true or t, when you set t to something, then you're saying everything back like that. But once you do negative, you kind of have to push it back because basically now you don't have t going further. Okay. Yeah. All right, I think that'll work. Um, and if size is less than m, you update this one. Okay. You have the additions. For the additions, you don't do anything. Actually, you do. You you want to add to t for addition. Oh, what did I just do? Okay, but hold on. Let's get to this. So first off, if m is less than or equal to size, you want to print no. Because, yeah, you're about to say it's true. And now you're about to say t is equal to t is equal to size, right? Yeah. Okay. Otherwise, you can update t here, update m all the way here. And then as you kind of go through, as you add characters, you're going to get t will stay the same, but you're going to add characters to it. And then when you subtract characters, it doesn't do anything. But then if it gets uh, less than it, it'll start removing. So okay, let's think about that. So if you have characters, and then you're removing characters. I think I confused myself here. Okay, so for sizes plus, I don't think you do anything because as you increase size, t will stay the same, and as you increase size, m will stay the same. But if you get ch equals 0, then you want to update your m. You're basically going to say, okay, well, is m going to get pushed back? If t is 1, then you want to update your m and just put in arbitrary large and set t to size. So t will like, yeah, be a current size. Um, but when you're subtracting, I need to figure out what I'm going to do. So basically, if I'm subtracting and the size is less than m, then I'm going to set m back to n. That is basically I don't know anymore. Okay. Um, Other than that, like it was in effect if you kept adding and so on. It wouldn't touch him. This makes me realize that actually this check is I think m just needs to be false or true. I think it just needs to be I think it just needs to be false or true. So for instance here, oh no wait, what am I saying? It does need to be a marker. Yeah, it needs to be a marker because you need to know when you need to set it back to true. So basically by setting m to n, it's setting it back to is saying you're saying it's not necessarily unsorted, right? You're saying you don't know. It's not unsorted anymore. But here you're saying it's unsorted from M position, from M index, from M size. So unless the size ever goes beneath M, then you say it's not unsorted. But you say it's unsorted from M size. Okay. And this is just checking if you said. And so this one is saying it's sorted for less than T size, for less than or equal to T size. So it's sorted for this one, and you just say so sorted for less than or equal to T size, unsorted from M size, and not unsorted. Seems right. And this is not unsorted. Okay, so I need to think about when I delete characters, if the size ever goes beneath M, okay, you need to do that. If the size is greater than M, it like doesn't matter. What about like T though? So you say it's true. You need to keep reducing this one. Well, you only need to reduce it if T should be set equal to the min of size. You only need to reduce it if size is less than T. So like this, or just do this. Just say if size is less than T, set T equals size. Because now you know that it's just sorted for that. So this is actually the same thing as saying T equals min of T in size. But it can never be less than 1. I don't know what I'm doing. I think this works. Trying to think like a good way to check. I could print out M T and size. And maybe CH. Actually, I kind of want to know it at the end. So this is like, okay, plus 1. So it's like, it sets T to 2 because now it's like, oh, yeah, because the current size was 2. Okay. This one, M is 7. It says plus, which is, okay, plus. So I guess size 3. It says it's sorted, so you set t to 3, which means it's going to be sorted for anything. Then you delete two characters, and then t is 1, size is 1, and then it tries to say 0, but the thing is t is greater than or equal to size, so yeah. Over here, okay, so t is never actually going to be greater than size. So you just do t is equal, alright? Okay. That should be the same thing. So yes, no. The second case, it says plus 0, but it's like, yeah, that's not going to work. The next case, it just says 0, but that's not going to work because, oh wait, that is going to work. Okay, yeah, I do need to say greater than or equal because of when it's 0, right? It could be 0. This is an example when it's 0. And then you have this one where it does a plus plus, does a 0, so it sets m to 2, and then it does a minus, but because of the minus, yeah, you can remove and put m to 9 again, like you don't know anything. You do the plus, then you can do 1, which is fine. Then you do minus, plus, and then you just set m to 2. Yeah, basically you're making sure that m and t don't ever like, and there's always m always has to be greater than t, basically. And then this one it does like a plus plus and it says but m, then it does plus minus. So m is still 2, and then it tries saying that it's sorted. But it's like, no, I'm not sorted. And then this one, plus 1 minus plus. Same scenario. As it tries doing the minus and then this plus here. And then it tries saying it's unsorted. Okay, well that's can't be possible. Let me give it some test cases that are going to be helpful for me to understand, such as add few. So let's add 1. Let's add plus. Like, yeah, these should work. Yes. Okay, these should be yes. This should be, oh yeah, this is yes. Okay, I guess I meant to add 2 pluses. Yeah, that should be yes. Now it's going to be no. Okay, I think this will work. We'll just submit it. There's a lot of ways to mess up this one. And we messed it up. Okay, I did mess it up. What does this actually tell you? Wrong answer on test 3. Let's try drawing this out, I guess. Okay, so my argument is that you can set a t and m, and as long as they don't like intersect, that's possible. That's reasonable. And so the size could be up to here, and you can know that it's false since M and it's true for everything over here. And then, as you add elements, it doesn't do anything. But if you subtract elements, and let's say you go over here, it's gonna, it will eventually, if the size ever becomes less, it will like remove this M. Um, but if it doesn't, like if it ever tries to update T, um, it won't work. Yeah. Okay. So if it ever tries to update T, it won't work. Um, There's only like, oh, if it ever, but yeah, let's say you remove the M and then it tries updating T, then it's going to be fine. It could move T to here, it can move T to here, it can move T really to anywhere. When it deletes characters, it pushes T back. What do I mean by that? I mean like if you have the size is less, this T will be moved to here because um yeah, but T is always going to be greater than 1. Hmm, what am I doing wrong? Let's see. Okay, let's try another test case. Let's try one here. I'm gonna do 8. I'm just gonna add test one. Let's do one here where you have a bunch of pluses and you do 0. Yeah, I mean, that's definitely true. You can return yes. So what if you do a 0 then a 1? What about a 1 then a 0? Yeah, those are true. You can't say it's sorted and say it's unsorted. Mm, and M can always decrease. Okay. Uh, mm, hmm. So it's checking if T is greater than or equal to size. And it's checking if M is less than or equal to size. Mm, Um, Dang. These are all correct. I don't like this. Because, yeah, you increase the size. As soon as you go back to 1, it's always guaranteed to be sorted. Like, it seems to do what it's supposed to do. I don't know how I could be wrong. Let's say you have a bunch of 1s. Let's say you have plus, and you do 0. What's that gonna return? Yeah, I know. And then this. Yes. Is there a way to make t and m equal? No. Because if t is greater than or equal to size, it won't do this. So only if t is smaller will it update in m. Okay. Let's think about this. Right, it's true. If you know it's sorted here, you know it's sorted throughout that whole array. So unless you remove those characters, you can update t and move it back, which is what I'm trying to do. Um, t is 0. T is 0. Shoot, I just found a bug. Okay, I found the bug. Okay, hold on. T is 0 right here. Okay, here I'm setting t equals size. What if size is... Oh, no. It's got to be this. Basically, you can never let it go under 0. Okay. It's like those small bugs like that. It's hard to find. And like it can hurt you so much. Probably... I could have wrote this, I guess, more concise. Okay, that was accepted. I only have 30 minutes left, so it's kind of pick or choose my last problem that I want to do. Like, do I want to do D? Do I want to do E? Do I want to do F? But a lot of people were able to solve D. Non-intersecting sub-permutation force suits. It kind of depends which one I find most interesting, maybe. Is it A, B, C, D? The number of cards in the deck is just by int. So that means you can give each player n cards. No, sorry. Number of cards in the deck is by n. That means you can give each player equal number of cards. Like it could be 2n, 3n. You can give 2 cards, 3 cards. Oh, but they're gonna give it so that every player receives the same amount of cards. Uh, what does independently mean here? They choose one of 4 suits independently and discards all cards from their hand which do not belong to their chosen suit. So like independent of each other. Okay. So without knowing. Like it's just saying that if player 1 chooses suit A, player 2 chooses suit B, he's doing that without information that player 1 picked suit A. Like these are just like independent events. Um, they discard all cards from their hand which do not belong to their chosen suit. And okay. So the better you do, the worse your opponents do, the better you can do. Yeah, so if there are multiple players, everyone gets 0. So they will definitely, okay. So for each player, what does this mean? Let's see. I think Okay. Let's go over this. So that was 2 hours, and okay. So I was able to solve 3 out of 6 in 2 hours. Um, and I guess I really solved three. I solved the three problems, and I still had 30 minutes remaining. And that was with a bug that took like 15 minutes, 20 minutes to resolve for C. Guess if we look at like the standings, just get an idea of where it would put me. Oh wait, isn't it? It's not gonna show it because I did virtual. Okay. I mean, it's not gonna put me that well. If we look at these people at the top, they were able to solve all 6. Wow. I mean, he solved all 6 in less than an hour. I can't even imagine how that's possible. Um, okay. I mean, he just left, I guess. He's, he was also on track to solve all 6 in an hour. I guess he just left. Okay, so some of these people, they just didn't even try the last problem, but they probably could have solved it. I don't know. Mm, hmm. How far is 200? So, yeah, if you wanted, so apparently all these people were able to solve these 4 problems in 2 hours. That's crazy. Um, so apparently they were feasible. Um, it's I guess let's go over them, and then yeah, I'm just gonna go over each of the problems. Okay, so A, prime deletion. The approach here was to just brute force it and just use a bit mask. I think my code is still here. Yeah, so prime deletion, uh, the goal is just to do the bit mask since there's only 9 digits and just create each mask and track the length because there's a length requirement had to be greater than 2 and construct the number. So kind of like a construct the number and check if it's prime. So it's like check every possible configuration of 2 or more digits, every possible subsequence, you could say, and check if it's prime. And that is good enough because this is square root n. This algorithm for checking is prime is square root n, and this is going to be like 2 to the 9, which is something like 500, around 500. Um, so it should be fast enough regardless. The other next problem is this one, binary strings, two binary strings, and the way that I solved this one was doing a dynamic programming and just storing, basically like storing zero and ones where both of the strings agree, store 0, 1. If they disagree at that index, store 2, which just indicates a disagreement. And then for the DP, you like will set your states as true. And um, if it's if the array, so basically you do the DP on this array that you create, and then on this array, if it's equal to 2, just ignore it. Like just leave it as false because DP is initialized false. Otherwise, just it'll continue. So if the previous one was true, it'll pick that one up and make the current one true. If the previous one was false, it's going to continue the false. So it's just continuing wherever the previous value was. If it's true, there's not really any reason to continue. And then the point of this is to basically find if there's a previous element that's equal to the current element, because then you can make everything equal in that range. Um, and you can make everything equal in that range in both of them. So you're just checking that. And you also want to check that it's true in this previous one, because if it's not true, there's no reason to do it. And if you can do that, then you can get true up to the ith index, and then you can break. No reason to continue the search. And then yeah, I'll just print yes if you can get true to the end. Um, I'm going a little quick just because there's so many to go over. And C was okay. C was queries for the array, and it was just checking that these are valid sequences. Um, basically that these are valid. These could be valid statements, or yeah. Um, basically the idea is that the plus adds an element to the n, a subtraction removes an element from the n, and the 0 or 1 is going to indicate if it's sorted or unsorted, or at least that's what monocarp is declaring. He's declaring that it's sorted or unsorted. However, it's possible that it's an invalid sequence. Um, that is like you add a bunch of elements and you say, oh, these three elements are sorted. Then you remove two elements, so you have one element remaining. Then he's saying it's unsorted, but that's impossible because if it's less than two elements, it's considered sorted. So something like that. Um, and you can do this by um, you can do this just by kind of keeping track of like two pointers. You have a pointer for sorted and a pointer for unsorted, so like a P1 and P2. And what you can do is you can say like um, you the pointer for sorted, like this is a pointer for sorted, this is a pointer for unsorted, um, and you have an array of elements, so something like this. Um, and basically, um, P1 is like here, and maybe P2 is initialized to somewhere like far off, like longer than the array. Um, and P1 is set to here because it's always going to be a set to 1 at least. Because if you have one element, it's always going to be sorted. So P1 can never go below this. But if you kind of just add elements and you increase your sequence and you get to some point here and then he's monocarp declares that it's sorted, then you know that everything is sorted that's less than it. So you just set P1 to here, basically, and now you know that everything in this range is sorted. And then if you ever sets P2, um, like let's say he says unsorted at this point, unsorted is different. Unsorted does not mean it's unsorted back here, but it means that, and like in here you may not know what's going on. You don't know, and it doesn't matter. But you can always update the information. So that is like if for some reason in here he returns a 1, now we can update P1 to be here and say, okay, well now we're just saying all of this is sorted. So those updates are valid um, based on the new information that he provides. But if you say P2, like here, you can say P2 is here. You say this is unsorted. What you know is that if you add elements to it, any element, like if you add up to here, these are all going to be unsorted, anything greater than P2. And but anything that this size is still unknown. Um, but it can be updated. That is, P2 can move backwards if for some reason you delete elements and then he says, oh, it's unsorted here. So this is the basic thing is that P1 can move in this direction, P2 can move in this direction. Now, when P1 and P2 are like this, that's when you have a problem. That is, if he's trying to say that it's sorted here, then right here there's a contradiction. Like he can't say, oh, the P1 should be here. It should be sorted up to this index when you already know it's unsorted from this index. So or from this element. So that's when this happens. So you're looking for these like basically this type of you're looking for this when P1 becomes greater than or equal to P2. Basically, this is impossible. And these values get updated, etc. And like whenever you do deletions, these can decrease as well. So like if he added a bunch of characters, like this, and he said, "Oh, hey, P1 is right here. That means I know it's sorted here." If you start removing characters, you can move P1 back because now you know it's sorted up to here. And then if he adds characters, you don't know if it's still sorted. Like let's say it's 1, 2, 3, 4, and you say, oh, P1 is here. He says it's sorted, right? Which means we can assume that this could be 1, 2, 3, 4. We don't actually know what it is, but you just plug it in. And then he says he removes this one. Um, so then, in a sense, P1 gets pushed back. Now you know it's sorted up to here, and then he adds another element here. He doesn't have to add an element. He could add it with a 2, which will make it unsorted. So then it could update and could say P2 is here. So it starts being unsorted from here, and this is a valid state. But then if you go further and add some more elements, etc., even if they're sorted, and then declares this is sorted, this is a contradiction because we knew it was unsorted from here. Um, but yeah, I don't know how clear this explanation is, but that's was my approach. This is how I coded it. I think I could have written it in a cleaner way because like you're just looking for intersections. Yeah, I could have maybe coded it in a cleaner way, but that's the 3 problems that I actually like wrote code and solved. For problem, I'll talk about the next 3 problems I didn't solve and how I think how you can approach them. Sorting by multiplication, I believe you can use some idea where like if you have a range where they're strictly decreasing, you can just do one operation to get them to strictly increasing. So I think you can do that, and then whenever you have like and then when you start getting elements, you can start increasing. I think you can use like just that basic logic. Like, oh, if you have strictly decreasing, you can always flip that, or you can always like I think maybe it's like a prefix idea. Like you can always say I'm gonna flip up to a certain range. Um, like it doesn't make sense to. It only makes sense to flip this because it's strictly decreasing from the start. But if like there was a strictly increasing part, I guess before it, um, I guess I'd have to think about that some more. So that could maybe cause an issue. I might go over this problem. I'll go over this problem again later, but um, yeah, like you can maybe deconstruct it into strictly increasing, strictly decreasing segments, as you say. You can maybe break it down into like uh, partitions or segmentation of it, and just you have these segments here. And what's different is that each of these segments are either going to be strictly increasing, or they could be strictly decreasing. And you can have like consecutive ones. Like this means like if you have 1, 1, 1, this is technically a strictly increasing segment, and this is a strictly increasing segment, right? So that's what I mean there. So you can have like so you can have adjacent i's and you can have adjacent d's. So these just represent strictly increasing segments and strictly decreasing segments. So the thing is that um, because there's a partition here, that means the two elements here must not be strictly increasing, which means most likely you're going to need to multiply this range, right? Right, you're going to have to multiply this range. And like, let's just say all you have are strictly increasing segments. Let's say you just have some stuff here, and let's say you have it's just consisting of i's. Let's solve this edge case first. This one you could just do. You just have to multiply this one, this one, and this one. But what you could do is you can imagine it's multiplying this entire range, and then this range, and then this range, and then this range. So I would argue one, two, three, four operations. I think that has an example like this. This one can be represented like that. You have one, you're gonna have one, two, three, four. So you have four, and you're gonna need three operations. Perfect. You have one, and you need zero operations. So yeah, if it was just strictly increasing, you just need to count these strictly increasing segments. Say one, two, three, four, five. I have five of these, and the answer will be four. So the number of strictly increasing minus one. But that's if it's consisting just of i's. But if it consists of d's, oh, that makes it more complicated. Let's do a case where it's not mixed up. Let's say you just have some d's here. What would you do in this case? You would do you can multiply. You're gonna have to multiply. Uh, these are strictly decreasing. Okay, so you need to multiply everything by -1. Or by, yeah, you need to flip everything. And then what you need to do is you need these to be more negative. So you need to multiply this range, and then this range. So okay, you need ND operations if it's just made of just like strictly decreasing segments. So like for instance, if it's 5, 4, 3, 3, 2, 2, 2, 1, right? Okay, so I have 1, 2, okay, I have these. So you can say, okay, how can I flip these? I can multiply everything by negative. So I just put everything as a negative. And then all I have to do is do like the reverse. That is, I need to multiply these. I need to make these more negatives. I need to multiply this range. So that way this will be larger than this. And then I can multiply this range. And then I can multiply this range. So that guarantees this to be larger. So yeah, in D operations, I think. So that brings me to how do you deal with the combination of both? No, like, wait, is it, so when you multiply by, uh, I'm trying to think here how you could do this. Because if you make these negative, then this is not going to work. Yeah, it kind of sucks, here because in order to make this increasing, you can go element by element. Okay, yeah, so here's what I'm gonna say. I'm not gonna go through this entire problem. Um, but I mean I will. I might do a separate thing on that, but basically you can approach it like this, and I think you can come up with a solution with this approach. It would just take like 10 minutes or so, or 20 minutes of just, for me at least, to just what's the word? What is it that I'm doing? Go through all the possible scenarios because this combination is it's not too complicated. Like but it's just you're gonna have to choose between making changes to each one or making changes to like the wide scope. So it's definitely gonna be dynamic programming. Like these are very simple scenarios, but once you start mixing I and D, it makes it just slightly more complicated. Like you have to deal with that case and if D is like the prefix, you can do this, and you can do that. It's probably the final solution would be some type of dynamic programming solution, but you got to be doing it in linear time. So right now I'm thinking of more of a oven squared solution. So I might have to also think of. I think that's what I'm thinking of right now. So I also may have to think of a optimization, or maybe a slightly different approach. Maybe some type of greedy argument can be made. Okay, I'll go over E. So E is non-intersecting subpermutations. So it's just asking, like K is between 2 and 4,000, and like N is between 2 and 4,000, and like, so you have an array that's going to contain 1 to K elements in it, or it can. That's the thing is that this is where the problem changes. This is a counting problem and counting the number of array. You want to calculate the sum, so you're kind of counting these costs. Um, but this first example, 2 is 2. It's best to understand these by examples. You have 2 is 2, and 10 3 is, wow, really large. Okay, so that was the 2 2 one is this case. So n is 2 and k is 2. So the possible arrays you can have are 1 2 1 1 2 1 2 2 because you can only use digits 1 and 2. And the only ones where you have contiguous subarrays where it contains both 1 and 2, that is 1 to k, is this one, 1 2, and 2 1. So you have two subarrays here. In fact, if you think about just two digits, if you think about n equals 2 and you think about k getting larger, well, k can get larger in front than n, I guess, in this case scenario, but I was thinking of some type of dynamic programming approach where you know that the first two characters are always gonna be like one and always gonna be a digit between one and k. So you always have uh k choices for the first digit and k choices for the second digit. So that's just k squared. So I figured there's always k squared possible configurations. And you can kind of see it's gonna go 4, 9, 16, all the way up to 4,000 square. 4,000 square configurations is like 16 million. So, worst case, you're getting like 10 to the 7. So I was like, yeah, maybe you can start with that, and then you could consider the next case, which is you're adding an element between 1 to k to the end of all those previous configurations, and maybe you can know how many of those form a subarray. But yeah, I don't know. I feel like something like that might work for this. That's about as far as I got. Mm. And this problem F is force suits. This is like I'm not certain what type of problem this is. Well, I mean, yeah, you're given these decks of cards. It looks like first off it has like a really long description, so there's a lot of words to read through, and then you kind of have to figure out how to solve it. I think it's some type of algorithm, probably dynamic programming, but you have to find the pattern first and figure out what is you're doing exactly. So like I didn't really figure out what I was need to do exactly. I think I did try. Did I write anything down? I tried. Yeah, I tried here. I tried writing like an example when you have 20 cards. Like you can just think. Um, yeah, there's certain ways to maximize score. I'm not going to go over this one actually that much because I don't really have too good of an idea. Like I'm thinking. It does give you like a really long time up here. So that's useful. So like you could probably get away with this. Like these are 10 to the 6, um, and this is 10 to the 4. So like you probably get away with something like here. Hmm, I don't know. You can get away with some algorithms. So you have to probably design some algorithm for this one. But I don't really have any good ideas. Okay, I think that's what I'm gonna go over it. That's what I'm gonna go over. So yeah, 3 out of 6. Probably could have solved 4. I think D is within uh my reach within 2 hours maybe. Although I think it is rather hard. And then E is where it starts getting really hard. It's a counting problem for sure. So you're probably gonna use some combinatorics in it as well. Some knowledge of combinatorics and whatnot. But and then force suits, I think only 8 people solved this, so it must have been quite hard. I'm not sure what algorithm would be needed. I'm not sure. I think you first have to explore what it is that you want to do for each one. Because, like, you have n players. So for each player, you can look at how can you possibly maximize by distributing the cards. You know, I feel like there might be some greedy arguments you can make. Um, or you could try each 4 states, and you could try giving. You want to give them as much cards as they need for each of the 4, and then you have to distribute the cards somehow. I think that's the trickier part. You have to figure out how to distribute the remaining cards to the other players such that they don't ever exceed him in any other suit, and that you give as few as possible to the suit that he's trying to maximize on. Something like that. But I don't know. It could be, yeah. Okay. Yeah, okay. That's it. I'm gonna end this now. Thanks for watching. Um,